Hi there, and welcome to another episode of Draw, Make, and Code. I'm your host, Ed Cavett, and in this episode we're going to be making a grid of Perlin noise waves. For coders who are familiar with processing and p5.js, just the title alone will tell you what the code is, the procedures, and you just need to structure it to produce the desired output, and it's pretty straightforward for most people who've been doing this for a minute. But if you're just figuring this out, if you're just learning functions, you're just starting to get confident with building your own functions or converting short procedures that are standalone code, converting those into functions, then this is the video for you, because that's what we're doing. We're going to the p5.js website, we're going to the example page, we're grabbing that noise wave example, we're going to take that and smash it down into a function, or even better, a method inside that function, because now that's going to give us a tool. So wherever in our generative art we have a line that goes from point A to point B, a straight line, now we have an object that can draw a noise wave from point A to point B. So this is a pretty powerful tool, and if you do it just right, it's going to be modular, so you can plug that into any of your generative art that uses a line. Instead of drawing the line, you just execute this function and pass into it a starting point, an ending point, and an incrementer. So as a tool, this is going to be really powerful and helpful in creating some awesome generative art. In the output that you see here, there's just one instance of that wave, but there are parameters for drawing proportions of the canvas and putting in each one of those proportions or those areas a line that's drawn like a noise wave. So when we persist the output like you just saw, it gets oversaturated and you can't really see what's going on. So we can work with the colors to fix that. Also, if we're smart about it and we draw our wave where half of the wave is to the right of an origin and half the wave is to the left of an origin, then we can rotate that wave around a center point and get it to fill the screen in a really cool way. So that's something that we want to do when we're building this object. We want to be sure to output it so that the 0, 0 origin is at the center of the wave. Then we can just take proportions of the canvas. So this is a 2x1 output, and if I keep adjusting the numbers there, I can get a 4x2. I found that in proportioning the screen that if you have a 2-to-1 ratio for the X and Y, that you get this nice columnar output. And the cool thing about it is that it's being generated by this kind of randomness, this blobby, irregular geometry. And it's the accumulated output of that geometry that's irregular that creates the regular patterns of the columns. And I think that's what makes it some compelling output. So play around with that. You can keep dividing the screen up and dividing it up and get these really, really small waves. Just keep in mind that the more objects that you're processing, the longer it's going to take to see your output. So your computer may not like it if you have a lot of parts here. So I keep the numbers down to something that, first of all, you can kind of see the distinctiveness of each unit, and you get to see the output sometime today. So that's kind of the sweet spot there. If you draw some regular geometry around each one of those areas, so a box around the proportional areas, and put the wave inside it, and then you can rotate that area, and you're getting an emergent pattern from the rotations and how they look collectively. I'm also using Perlin noise to shift through the colors, and you can persist the output or just watch the refreshed output because it's all pretty cool. But if you persist the output, then you start getting a really neat interplay between the regular geometry and its emergent patterns and the irregular geometry as it takes away from the regular geometry. So we're going to get to see a little bit of an example here. And the way that changes over time I think is really fascinating. So you could take a still of any one of these outputs, but I kind of find that in some generative art it's a lot nicer to see it over time, so kind of like as a video output. And the way that this works over time, I like it a lot better than just a single image. So depending on what your goals are, if you want to watch this over time, the output may be more compelling that way than if you just take a still. So kind of keep that in mind as you're generating your output. The variety that you get in output means that anybody could make this their own. I'm sharing this with hopefully lots of people, and each one of you are going to be able to create something that's going to be distinctly yours. Even though we're using fundamentally the same procedures, if we plug in different parameters, we're getting different outputs. So based whatever your aesthetic is, you can put it right into this code and do some amazing things. Plus the components can stand alone. So now you have this noise wave tool that will draw a noise wave line wherever you have a line in some art. So that's something that you can start thinking about in the design process. Now you have one more tool, one more process token in your process structure. Hopefully you're pretty excited and you're ready to code now, right? Well, if you are, fast forward a little bit, because in this last little bit of the introduction, I wanted to show you some variety in the output. Again, you can make this your own real easily, and I'm going to demonstrate that here. And as I do, I kind of wanted to talk about the artwork itself and what are some of the aesthetics that I really appreciate about it. The columns, the uniformity of the columns to me reminds me of like some structure. Like you could think of it as almost a board, right? And then the irregular geometries that make up that board, that evolve out of the persistence of output over time, that looks like different, the way that I've colored it looks like different pieces of wood. So this kind of looks like intarsia a little bit. And I like that blend of taking an idea that's done in woodworking and extending it into the generative art dimension. So that's kind of what I was going for when I picked my color scheme, is to push it into that context of intarsia, where you have different colors of wood that are together that form a mosaic constrained by some recognizable form. And to make things easy for me, the recognizable form is just a simple column or geometry. I found by adjusting the different proportions that I could get something really cool to come out of a 2-to-1 relationship, and I like the columns a lot better than the rows. If I rotate smaller proportions, or I guess it'd be larger sections, but the proportions are smaller, so like I think this is maybe 4:1 or 6:2, something like that. What's it say there? 8:2. And then if you rotate the wave inside there and erase that output using a regular geometry, it can create this emergent geometry out of the white space. So then you're starting to play with what you're taking away, and that's producing something itself. So just some ideas and some tips there on how you can manipulate this output and get something really, really cool to come out of it. Just think about what you're doing, what you want to do, and code to that. All right, we're ready to code now, and we're only like a third of the way into the video, which is actually a good sign, because you know that this code is going to go by pretty fast. As I've typed it out here, I've added annotations for people who just want a little bit more information or a little bit more guidance. If you're seasoned, you don't really have to pay attention to that, but you're probably going to maybe run out of patience waiting for me to get to a single line of code after writing a whole paragraph about it. But I'm just trying to be inclusive to as many people who want to learn this as possible. So in the global space of our new sketch in p5.js, we're going to declare, but we're not going to assign, to some name we make up that's going to hold the object that creates our particle system and the method that produces the wave objects on those different particles in the system. In setup, we're going to use the available window width and window height, and we're going to set to that variable that we've declared a new instance of LineMaker, and that's just a name that I've made up for this function. And we're going to clear the background at least once, and we're going to set any geometries to their center. Then in draw, we're going to, if you want to, you can fade the background, you can watch it refreshed each frame, or you can persist the output. So I've commented out the background statement. The parameters there will fade the background nicely, but I've just commented it out because I want to see the persistent output. Since the first part was short and sweet, we know that the last part is going to be a little bit more involved since it's doing all of the work. So we're going to create that function called LineMaker, and you can name your function whatever you want. I just did that because it seemed like it made sense in my head. And then inside that function, we're going to have a method called this.update, and it runs through the array of particles. And then it passes in the parameters for those particles into another method called waver, and that uses those values to know where to put a wave at. And it's going to generate one wave, and it's going to go back to update. Update's going to go to the next point, send it to wave, and rinse and repeat until you have a complete matrix or complete grid of noise waves. So in the constructor space of our line maker function, we need to set up some arrays that will hold all of the particles in the system. And the particles in the system aren't moving around. They're tied. They have constant locations or fixed locations. And the way we're going to get those locations is we're going to loop through columns, we're going to loop through rows, and then inside that double loop, we're going to push into the array that location that's determined by the column and row value. And we're going to do that with a vector so that we can get an origin of 0, 0. And it's all going to be associated with its point in that grid. So we have an array that holds the anchor position. We have an array that will hold a variable position if we want to move our wave around inside that area, or if we just want to move points around inside that area. We have an array that will do that. And we also have a velocity to move that point by, and we also have a scale that's associated with the proportions that we've given to the screen. We're dealing in noise waves, so I wanted to have a global function variable to handle a y offset. I was using the frame count, but it doesn't work when you have a lot of processes that are happening, and it kind of throws things off. Then we're going to assign to some local variables our proportions, and we're going to give them the name columns and rows. We find our proportions for columns by dividing the width by some number, and for rows we're going to divide the height by some number. And those are adjustable. You can have sliders or inputs or whatever you want for those to have some interaction. We also are going to be assigning values in an array, but we're not going to be assigning them like look at value 0, put something in it, look at value 1, put something in it. Instead, we're going to just push values into the last position in the array. When we do that, unless we test the length of what's there already, we don't really know how long the array is or what element in the array it's on. So I'm going to keep track of that with a variable. And then when we do our loop, we're going to use the variables k and j. K is going to represent rows, j is going to represent columns, and we're moving through the rows and columns by an increment that's defined by the local variables that we gave the proportion to, so rows and columns. Pretty much a standard incremental loop inside another standard incremental loop that's of our proportioned canvas size. And then inside the center loop, or it would be the columns loop, we're going to push into the arrays the values. So we're getting an x position from one of our loops, we're getting a y position from our other loop, so we're putting that into the anchored position. And then we're going to set our geometry to the center of that anchored position. So it has a vector of 0, 0. To get some variety in the output, I'm going to set to a local variable a random vector. And then I'm going to multiply that times some noise return multiplied times a magnitude of some sort. So in this case it's 3. And then I'm going to push that into the velocity. So if you use that variable, I'm not sure that I use it here, but if you use that variable, that's some way that you can get the movements to be relational through noise. And then we get our scale x and scale y that come from the proportions. And since we're splitting that from the origin, we're just going to take half of that scale. And then when we use that, if we need to have the entire length, we can double it. But we're actually going to be using like negative scale, positive scale to get the full length of the line. And then we push into the y offset, that index value, and that's going to be used to multiply some kind of noise value. And then if you want to rotate things, you have an array variable for that. So next is update. An update has all of the heavy lifting. We have all of the arrays set up, ready to go. We just need to move through that array, or move through those arrays. So we're going to have a loop that's the length of one of the arrays. And since they were all created at the same time in the same loops, they all have the same length value, so we can just use one of those to find the length of that array. When we created our arrays, we could have created another array that would hold the normalized value for our columns and rows. So the first column would be 0, the second column would be 1, so on and so forth, even for the rows. Well, we don't have those values, but you can use a formula to get it from a loop that's running through the index value. So you just use that index value, you perform these formulas, and it will give you the normalized value for your columns and rows. And we need that because if we're going to have relational values based on the position of any object in that matrix, then we need an x and y value to put into the noise parameters to get that relationship. And that's what we do here. I'm taking the map, the interpolated value that comes from the return of noise, and that has the x, y, and z accounted for, so kind of like 3 dimensions. And z here is kind of time. It's over time, so it's not like a depth dimension, it's just a time dimension. And I'm doing that for 2 different colors, for red and green, and then I can play around with those in the statement itself to get this relationship that produces the brown with the red and yellow tones. So once you have some color, and the procedures for getting color can be pretty involved, but once you have some colors, then we can put those into the graphics attributes. We can play around with them a little bit with some formulas inside there if we want. We can use fills, no fills, closed lines, whatever you need there. And we're going to isolate everything in push and pop, so when we drop out of that, we're going back to the default origin. And then when we go inside push and pop, we're back into wherever we're translating to. And that lets us isolate each one of those proportional areas and work within it as if it was a regular canvas. And the center of that canvas, the default, is going to be the 0, 0, but it's going to be placed at the center of that area. Do your fills, do your strokes, your stroke weights, and then once you have all of that planned out, I think I even include here a rectangle geometry so that you can bound it and start playing with some of that as well. It's commented out here, but you can turn it back on and do whatever you want with that. Once we have all the information that we need that describes our particle's location in the grid, then we can pass that into the method that's going to create the wave. So we have to tell it where the wave is going to start, where the wave is going to end, and what wave it's drawing in this matrix. So when we get to the method inside this function that's going to produce the wave, it's pretty much the example from the p5.js website. In that example, the wave is drawn from 0 to the right hand side of the screen, and those values are kind of arbitrary. We could put anything in there. So if we pass into a method the beginning and end and just plug those into the loop that's inside this example, then now we've got a lot more control over that wave, not as an object or a program that fills the screen with a wave, but now it's a tool that we can use to draw a wave wherever we need a line. And I think that's pretty powerful. I'm really excited about it because I haven't used this tool very much yet, and I have all kinds of plans for it. So I hope you get the best out of it too, and if you do make something really cool, please leave a link in the video or message me on my social media. I would love to see that. So in this method, I'm just going to set to some local variables using the parameters that were sent into it, where the top is, where the bottom is, where the left and right are, I guess beginning or end. And now I've got these easy variables that are clearly labeled to use inside this noise wave loop. So we're going to do our begin shape and end shape, and then we're going to make some vertices inside that bracket, inside that block. And when we call end shape, it's going to draw a line between all of those points. And this is how we create shapes in p5.js. So we're going to do our loop, and the loop's going to have the start and end parameters, and it's going to take a proportions of the end value, which is basically the size of the wave. So we're incrementing through that wavelength 1/10 of its length each time through this loop. and then we advance the y offset. We plug that into the interpolation of a noise wave. We give the value that's returned to a variable called y. We have x from our loop. We have y from this local variable that's from the noise wave. When we put those two values in the vertex, it's going to chain a length of points in this wave shape. So pretty much how a noise wave works. If you're familiar with the example, or if you've just looked at it, that's kind of like that's how it works. I hope that has helped any and hasn't just served to confuse you further. To get the y value, when we're using the interpolation, this map of noise, we're going to use just an x and y, so two-dimensional noise, and we're going to get a top and bottom from that. So we're not using 3-dimension like we were with the color, we're using 2 dimensions because our noise wave is like a 2-dimensional shape, and over time comes from the change in the y offset. So we make our vertex there. Now it knows 1 point in this wave line, and then we're going to advance the x offset, and depending on how big or small that value is, you're going to get wild, crazy noise or really mellow, chill noise. And if you adjust the y offset, you're going to get it happening either quickly or slowly. So that's kind of like your time variable. I think that's how it is. If that's not how it is, just switch what I said around and you'll figure it out immediately. So when we call that end shape, it draws the wave, and it's going to draw it in that proportional area. And I think that's it, so let's press play and see what happens here. Okay, let's see what I did here. Looks like I misspelled something. So let me scroll all the way through this and try to find where that's at. That's right. Here we go. Seriously, just one mistake. That was it. It's working now. That's pretty amazing. That's good for me. If you've watched my videos, you know that that's really good for me. So I hope you've had the same results. If you haven't, the code for this program is available in the description. There's a link there that will take you straight to the output, and then you can just click on the title of that program to go to the code. Let me know what you think. If you have any questions about what I've described here, I'd be happy to answer those as best as I can. You never know, they may inspire another video to clear things up. So if you found this confusing, if it didn't help you very much, please let me know, because I may be able to fix that and help you achieve your goals of making this program. So I hope you'll do that. Well, I guess that's it for this video, and I wanted to say, if you're new here, if you're newly subscribed, thank you so much for the support. I hope to continue to produce output like this so you can continue to learn and enjoy coding and the art that it can create. If you haven't subscribed, I'd be honored to earn your subscription. Hit the bell to be notified every time a video comes out. I try to produce content every week, and at least one tutorial a month. So it's not a ton of content, but there's enough there to where it's worth subscribing. So I would be honored if you'd support me there. Let the algorithm know that this is content that people enjoy and that they're engaged in. So leave a comment, hit the like button, and that's going to get this out there to more people who are in traditional art media, who want to learn more about generative art and maybe discover that it's not so hard or impossible. It's something that I truly believe the average person can do this. They just have to learn the steps and be encouraged and have some help whenever they meet up against some challenge that confuses them or they just don't know how to get through. So let's do this. If you're an artist and you want more people to know about this, then that's the way to do it. So hit that thumbs up, leave a comment, hit subscribe, hit the bell, do all of that stuff, and it's going to go a long way to accomplishing your goals of sharing this with others and my goals of making sure that as many people who want to learn this know about it and can have access to this information. So I guess that's it. Until next time, thank you so much for watching, and take care.